Hello everyone, welcome to Dewesoft Sound Power webinar. Today we will focus on how sound power measurements are conducted and why they are so important. You will learn about different suitable applications and supported ISO standards within Dewesoft Sound Power plugin, as well as how to differentiate between individual standards in order to choose the right procedure for the job. With our newly acquired knowledge, we will set up our measurement system and perform a simple sound power measurement at the end. Perhaps we should begin by establishing what sound power actually is. Sound power is the total energy radiated by a noise source in all directions. We measure sound power in watts, which is a unit of usual power also. And sound power is a property of the sound source itself. Therefore, it is useful for rating and comparing different sound sources from each other. A useful analogy from electricity would be what electrical power is to temperature, sound power is to sound pressure, one being the cause and other the effect. Now that we have briefly established what kind of physical property sound power is, let's focus for a moment on how sound power is measured. We measure it through an array of microphones, which all cover their corresponding surfaces, depending on the shape of surface we are using. A special environment, such as an anechoic or reverberation chamber, is used. On our picture on screen, we can see a semi-anechoic chamber with insulation on the walls, but the bottom floor being reverberant. And the calculation principle for sound power is as follows. We calculate it through multiplying sound pressure with the particle velocity, which is known for our medium, which is of course air. And we multiply those two things with surface area. And the end result is the sound power of our noise source. So after discovering how to measure sound power, we should maybe shed some light on the fact which is perhaps the most important. Why is sound power measured and why is it so strictly regulated? To ensure health and safety of consumers and users, producers of almost any kind of machinery or devices are required by regulations to measure and declare the sound power of their products. And this holds true for anything from toys, printers, to white goods, industrial tools, and even construction machinery. In addition, sound power measurements are also used in engineering tasks such as product sound design, which is done in order to improve sound characteristics of certain devices and to make their noise more appealing to the user. As measurements in acoustics are carefully regulated by standards, sound power is of course no exception. In the next section, we will perform an overview of sound power measurements and the corresponding standards, to see how they are regulated and which one are supported within our sound power plugin. When conducting sound power measurements, we can either measure them through intensity or through sound pressure. We call one method intensity-based and the other one sound pressure-based method. Today we will focus on the sound pressure-based method, but at this point I would kindly invite you to our YouTube channel, where we have a webinar designated to sound intensity measurements as well. Generally speaking, when measuring sound power through sound pressure, we need a controlled environment, which is either a reverberation room or an anechoic chamber. Both create a special sound field. Reverberation room creates a diffuse sound field and anechoic chamber creates a free field. Diffuse sound field means a lot of echoes, a lot of reverberation, and anechoic chamber essentially means no echo at all. Below you can see which are the standards that are measured according to, that are measured in each of the environments. All of them are of course supported within our Sound Power plugin. And in the next section, we will focus on each standard in detail. Let's begin by going through the standards which are used in the reverberation environment. First important standard is ISO 3741, which describes precision method in reverberation chamber. Reverberation chamber, as we've learned, is used in order to create a diffuse sound field. Diffuse sound field is a field where sound reflects so many times that it travels in all directions with the same probability, which is shown in the schematics on the right. We can measure, according to ISO 3741, in one of two possible methods. One is direct and one is comparison method. The biggest distinction between the two methods is that for inputting the characteristics of our measurement room, we can, for direct method, use the RT60, which is a reverberation time for our room. And in comparison method, we use additional piece of equipment called the reference sound source, which is calibrated for sound power. So sound power of the source is known for each band. By measuring the pressure with the sound power, with the reference sound source put in our test chamber, we can also obtain the characteristics of the room. Above ISO standard is applicable to all types of noise, meaning steady, broadband, narrowed band, or discrete noises. All of those are suitable for such measurements. A minimum of 6 microphones is needed with this method, and the method is suitable for information technology and telecommunication equipment such as processors, controllers, card readers, and many similar devices. Those are only a few for an example. Moving on to the next standard, which is again measured in a reverberant environment, is ISO 3743-1, which describes engineering method in hard-walled room. The only supported method within this standard is comparison method, due to the fact that we are measuring in a room which has a lesser properties than, for example, a reverberation chamber. So a reference sound source must be used. Supported are all noise types except isolated bursts. And we need to use at least 3 microphones. They are placed at random positions. There is another requirement for the room property, and it's the volume, which must be greater than 40 cubic meters, and walls must be hard and strongly reflective. This sort of method is suitable for small items and portable equipment, such as vacuum cleaners, fans, electric shavers, and fan heaters. At the end of our webinar, we will actually measure an electric shaver. Very similar to -1 is also ISO 3743-2, which describes engineering method in special reverberation rooms. So -1 was for hard-walled room, and -2 is for reverberation room. Both direct and comparison methods are supported within the standard, and there are very strict requirements for reverberation chamber. The volume of the chamber for this standard must be greater than 70 cubic meters, and the specific reverberation time of chamber is required. We must measure with at least 3 microphones put at random positions. At this point, I would like to sum up the microphone positions for reverberant field. Whenever we are dealing with the reverberant or diffuse sound field, microphone positions can be placed randomly because the noise incidence is also random. Suitable applications for -2 are the same as before in 3743-1. And now that we have went over ISO standards that are described for measuring in a reverberation room, let's also focus on those standards that are for anechoic chambers, meaning free field conditions. First one on our list is ISO 3744, which is engineering method in essentially free field over a reflective plane. It's suitable for both indoor and outdoor measurements with one or more sound reflecting planes present. For example, the floor must be reflecting. A flat outdoor area with no objects located close to the source or a semi-anechoic room is considered to be perfectly suitable for the requirements. So 3744 must be measured either outside, far away from any surrounding objects, or in a semi-anechoic chamber, which was seen on the picture a few slides before. Device under test is enclosed in any of below measurement surfaces or combination between two of them. Number of microphones and their positions depend on the chosen surface and the measurement purpose, and they are described in detail in the standard. Such method is suitable for measuring non-electric handheld tools, such as all kinds of drills, electric saws, power saws, meaning hammers, riveting hammers, different hydraulic wrenches, and many other power tools, as well as IT equipment and household electrical appliances. And the most precise standard and with the most strict regulations is the ISO 3745, which describes precision method in anechoic or semi-anechoic rooms. It is suitable for all noise types, but has very strict requirements for high quality anechoic or semi-anechoic chambers. Meaning the environment used in order to be able to measure according to ISO 3745 must be of highest quality possible. Device under test is enclosed in spherical or hemispherical surface, depending whether we measure in anechoic or semi-anechoic chamber. Spherical surface is for anechoic and hemispherical for semi-anechoic chamber. Number of microphones needed to measure according to ISO 3745 is 20 if we position them at fixed position over our measurement surface, or we can measure with only one microphone where we must pass it for 10 circular paths or 8 meridional paths, or over one single path, which must be continuous spiral and has at least 5 circles around our measurement surface. Because this is the most precise standard, it's suitable for information technology and telecommunications equipment, which is also relatively quiet, meaning keyboards, copiers, PCs, and even ATMs can be measured according to 3745. At the end, we will observe two standard pairs, which are supported as well within our sound power solution, and they regulate measurements of earth-moving machinery measured in stationary test conditions. So according to ISO 6393, we measure the sound power level of our machinery, which is under no load, but all the attachments must be connected as in the production version. Engine must be operating at rated speed, and we use a hemisphere for this measurement, and we measure sound power according to ISO 3744. So this standard actually states ISO 3744 in regards to sound power measurements. Measurement is started and stopped using a designated trigger channel, such as light barrier, which is triggered when vehicle passes by. And 6393 is most often used in pair with 6394, which describes determination of sound pressure level at operator's position, meaning we measure with one additional microphone also the sound pressure level in the cabin where the operator sits. So this standard pair is suitable for all kinds of earth-moving machinery. This is only 5 examples. There is a lot more described in the standard. And very similar to the pair before, we have another pair which regulates, again, measurements of earth-moving machinery, but this time in dynamic test conditions. So again, we measure sound power level, but the machine is now moving, and measurements are made in either travel mode, stationary work cycle mode, or combination of both. We also measure over hemispherical surface, and sound power is again measured according to ISO 3744. We use a trigger channel in order to start and stop the measurement, and we use again additional microphone to measure sound pressure level at operator's position in the cabin. Suitability of this standard pair is the same as the one before. The only difference is that before we measured machinery when it was running on idle or prescribed RPMs, and now we have the machinery under work cycle. Okay, after we have performed an overview of supported standards and what are they used for and how many microphones we use, but how do we know which ISO is right for our task? Standards in previous sections only explain how to measure sound power, but do not state any limits on the levels generated by the noise source. Such limits for specific equipment are given by different additional directives and standards. Some of them are listed on the screen. Depending on the type of equipment we are dealing with and we want to measure, correct directive or standard must be respected. In addition, many ISO standards for sound power measurements require calibration of equipment according to additional standards. Most important of those being IAC 61672, which is for sound level meters, and IAC 61260, which is for calibration of octave filters. We are collaborating with an internationally accredited laboratory in order to carry out calibration of Dewesoft measurement solutions according to both of the above standards. So we can offer calibrated equipment according to the standards to our customers. And the fun part I was promising, the actual demo measurement. To conclude, we will perform a quick demo measurement of sound power level of an electric shaver. First, I will turn on my camera so that we can see how our measurement setup looks like. Okay, so we have 6 microphones positioned at random positions because this is a sort of reverberant field, and we will be measuring an electric shaver today, which operates at constant RPM, so to say, or with constant sound power. So in order to do so, we will open our Dewesoft software. Right, let's begin by checking our analog input settings. I am using 2 serious slices. One is a different input slice, having everything from ACC to low voltage and multi-ins. And I have connected one Sirius Mini as well using sync cable so that I can use both at the same time. I have selected channels according to my connected microphones, and I have previously calibrated all of them except the last one, which is on my table. I am using a GRASS 42AG calibrator for this task. Let's go to setup of the microphone. After switching on the calibrator, immediately we can see the signal supplied in the scope. So I simply press calibrate because I am using 1 kilohertz at 94 dB. And the software was already set for 94 dB. So the only thing for me to do is to position the microphone on our grid. Like this. And after calibrating the microphone, we can simply press OK. So everything is correctly set regarding our analog inputs. Let's now move to sound power plugin channel setup. I will be measuring according to 3743, and I will be using 6 different microphones. As we can remember from before, minimum number of microphone used was 3, but standard actually also describes the possibility of using more than 3. I have previously inputted the correct coordinates of my microphones, so this is pre-filled. We will measure in 1/3 octave, and we have set the octave spectra, octave calculation borders according to what is required in the standard. So according to ISO 3743, we can measure up to 8 kilo. We will be using A-weighted results today, and we will average the measurement for 20 seconds. We will not use trigger channel for today's measurement. Neither we will use history, and we will only perform 1 run. We must input the correct environmental conditions. So I will again switch on my calibrator, and which has also the option to read meteorological conditions. So I will just input what is shown here. The temperature is quite high, and the barometric pressure is a little bit lower than what is set by default. And we have a 29% relative humidity. Okay, so this is now correctly set. We would like to calculate background noise from measured data, as well as K1. And we will use first for the direct method a reverberation time for the room. I will input the approximate dimensions of the room, and we will just leave the reverberation time at 3 seconds. Okay, let's now move to measure. In predefined sound power screen, we already see the option acquire background. For acquiring background noise, the conditions must be as quiet as possible, but unfortunately, due to me being in an office rather than a suitable chamber, there is, however, some noise. We will perform the measurement as per standard, but please kindly note that the results will not be correct. Okay, we see the status of the measurement says that K1 background noise acquisition was finished. So now I will switch on my device under test, which is an electric shaver. And we will perform a measurement of sound power. We can see that acquisition was finished and sound power measurement was finished as well. System is letting me know the difference between sound pressure where source is on and when source is off is less than 6 dB. So background noise correction of 1.3 dB has been applied on bands with center frequency 125 Hertz. This is due to the fact that when we were acquiring background noise, the conditions was not quiet enough. Okay, so this is the end result of our measurement. Let's see how we can export our data into a predefined report. We will first deselect all of the channels as we want to select only single value channels in order to make the export faster. We selected MSXL and sound power for predefined report. We click export, and after the report has been successfully generated, we will receive a predefined Excel template filled out with all of the data regarding our measurement, as well as the result we are looking for, which is the overall sound power, as well as sound power on individual bands. Under single value, there are much more values exported, so we can use them in further processing if we need. And now, since we have a little bit of time, let's see how we can perform a comparison measurement as well. So when you acquire a reference sound source, it comes with a calibration sheet which states all of the sound powers output at certain bands. They range from 72 to more than 80 dB. So this data must be input in our software as well. So we will click RSS editor, create table, and today I will just put 80 everywhere. Okay, after we close it, the table is automatically stored. And the only difference in measurement would be that when measuring, we would first acquire K1, which is in silent conditions. Then we would put our reference sound source in our test chamber, and we will select K2 here and click acquire RSS, wait for the system to finish, remove the sound source, and then put our device under test in our test chamber. And then we will again select run 1 in order to perform measurement on our device under test as well. So this was a overview of what sort of standards we support in our solution, as well as a short, simple measurement with both direct and comparison methods. As you can see, our system is very straightforward and easy to use, and the software guides you through all of the necessary steps. Thank you all for joining, and have a great day.